This is Modeling Compost Efficiency by Ellen Dunn, Ben Bosler, Todd Kraut-Hamel, and Kayla Bursch. We decided to model compost efficiency using MATLAB so individuals can better create an ideal environment for a batch compost. So why is composting important? First, it creates valuable nutrients that can then be used to help promote the growth of more food in a garden. So it's basically food for our food. 2, it helps reduce the amount of trash added to landfills because it provides another outlet for the trash that you have that cannot be recycled and ultimately reduces the amount of landfills. 3, it's cheaper than chemical fertilizers because the materials that you buy to use for a substrate are natural, therefore they're much cheaper. And 4, it's a healthy and sustainable fertilizer for soil. It's great for the environment, great for your plants, and an extremely natural process. So composting is a really great system. The 4 main factors that go into composting are temperature, pH, substrate, and gas exchanges. So first, temperature. It's influenced by both the ambient temperature and internal temperature of the compost container. pH plays a large factor in the outcome of the compost and the microbial activity as microorganisms operate most efficiently in acidic to neutral environments. The substrate used plays a large part in the compost efficiency because it determines a lot of the initial conditions, and as you add more substrate to the compost during the process, it helps to maintain more homeostatic conditions throughout the entire compost process. Gas exchanges are also vital in composting. The main gases that are used are carbon, nitrogen, oxygen, and water. So depending on how much exposure the compost pile gets to these gases, the pile will have varying consistency. The final product of the pile will have varying consistency, chemical makeup, and other qualities that an individual may want to control. We have created a model that evaluates the carbon dioxide emission of a compost. So when the substrate decomposes, it releases CO2. So the amount of CO2 emission is a great factor off of which to evaluate the compost efficiency. So in our model, the main factors that can increase or decrease the rate of decomposition are the mesophilic biomass, thermophilic biomass, and substrate. The elements of the model that will vary throughout each trial are temperature, pH, and consumption of oxygen. And just to reiterate, the more CO2 emission relatively, then there's more efficient compost.
The mesophilic biomass are biological organisms that live in moderate temperatures and humidity levels. Growth rate of these biological organisms depends on temperature and oxygen consumption. Decay rate depends on temperature and the process of decomposition takes place in the mesophilic biomass will decrease in... I messed up.
Let's go. Just keep going.
So the decay rate depends on temperature and the process of decomposition takes place due to the mesophilic biomass will decrease into thermophilic biomass. The thermophilic biomass are biological organisms which live in high temperatures and humidity levels. These growth rates depend on the temperature, the oxygen consumption, and the initial pH, as well as the change in pH. There is no decay rate in the thermophilic biomass because as the process of composting takes place, an irreversible process happens where the mesophilic turns into thermophilic biomass. The substrate is the initial starting value of materials. A combination of mesophilic and thermophilic biomass ratio with a maintenance coefficient is used to determine their composition effects on one another. Also, this entails a growth rate of substrate proportional to the end yield of the compost. So to conclude about composting, it is a biological process that depends heavily on the surrounding factors. Whether the temperature is hot or cold, there's a lot of aeration or not much at all, or if the pH is high or low with the starting substrate. There are specific factors that can be changed to ensure the process is most efficient, and there's no specific rate in which determines maximum efficiency. Only analysis on many elements that change the compost can determine if one compost is more efficient versus another. Now we will go over the model that is used to code and represent the compost.
Okay. So for our model, we began with a program which we titled CO2_model, which begins by having the user enter the 3 parameters for our model, which are temperature, pH, and initial mass of substrate. So the first part here shows the inputs and checks whether or not the user inputted values are within the correct parameters for the program to run. And if they are not, then it gives the user an error prompt and asks them to re-input the values. And then it asks for the initial amount of mesophilic biomass and the initial amount of thermophilic biomass, and then the time, which is, I guess, down there. Then the program defines all of the values that are specified in the literature for the model. And next, the program will call 3 separate subprograms, each of which will use, this is also like this one, okay. Each of which will then use ODE23 to call another function, which within it is defined the differential equation for that specific parameter. So it calls each of those and solves all of them, and then we have a for loop here that combines them all, adds them all together, and combines them into finally the CO2 emissions. And finally, the CO2 emissions versus time are graphed.
Okay, so we're gonna run the model, and for the inputs we're gonna use parameters or from the literature for calibration, the calibration parameters from the literature, and the temperature is going to be 37. We enter that. If I had done anything under a certain temperature, it would give me an error message. Then we're going to do the compost pH, which has to be between 4.3 and 14. So enter 5. And the initial mass of consumed substrate is the amount that's per carbon, kilograms of carbon per kilograms of carbon into the model. So we'll put 1 there. And then the next is the mesophilic biomass, which is 1.6 times 10 to the minus 4. And the thermophilic, which is 1.8 times 10 to the minus 4. And then you enter the time in days, because this model is calibrated to do over time, but it's done with 100 time steps no matter how many days that you do it. So we'll put 7 days and run it, and then all of our graphs come up, and I'll go over them one at a time. First, we have the first graph, which is the mesophilic biomass versus time in kilograms carbon per kilograms carbon in. And as you can see, the mesophilic declines on an exponential curve. And if this were part of the bigger model, it would still be exponential, but the line would vary as the growth rate would vary according to time. The second figure is the thermophilic biomass, which goes up on a exponential curve. And again, like the other one, had it been in the larger model, this line would be exponential, but the rates would vary according to the growth rate. The third one is substrate consumption, and it's a linear differential equation. So you get a linear line as the substrate is consumed, it goes down. And then from the last figure, you see the CO2 emissions, and it's a nice curve. Starts out a little bit higher and then decreases a little as the two biomasses cross each other, and then starts to go back up. And we'll run it again, except this time we'll use some arbitrary values. And if I can find, there we go. And this time we'll use a 50 degrees and 4.8 and 2, and we use 4.0 to the minus 4 and 1.9 to the minus 4, and we'll do 7 days again. And as you can see, with the different parameters, you're going to get different values. The CO2 emissions drop sharply as the mesophilic biomass drops sharply. And then it begins to climb again as the thermophilic biomass takes over. So that's our model, and it's the
It's precise, but it's not necessarily accurate.
Yes. The model itself is precise, but it's not accurate as the CO2 emissions versus time. It wouldn't be as smooth a curve as this. It would start off lower, and it would eventually get higher as the different parameters change, as the temperature increases and the pH varies, as the CO2 varies. So this is the best representation for this submodel that we have, without having the other two, without having the physical and the acid model as inputs. But we believe that this isn't precise but not accurate model. So